We continue talking about sequences, and now we talk about bounded sequences. So starting with the definition, I say that the sequence an is called bounded above if there's a number m such that an is less than or equal to m for all n greater or equal to 1. Okay. So it's like m is an upper bound for all the values. For example, if I consider, let's say, an equal 1 over n squared. Okay. You know, if you list the terms of this, a1 is equal to 1 over 1 squared, which is 1. a2 is 1 over 2 squared, which is 1 over 4, and so on. So you're going to see that you have 1 over 4, that's the terms of the sequence. You have 1 over 9, and so on. So you can see the pattern, you can see the sequence, you can see the behavior, and you can see the most important part is that for every value here, an is less than or equal to 1. So in this case, I say that this is bounded above, and it's bounded above by 1. So this is m in my definition. Similarly, I say that an is called bounded below if there's a number m so that an is bigger than this number for all n greater or equal to 1. We say that it's bounded if it's bounded above and below. So once they say that an is a bounded sequence, then you have to assume that it's between two numbers. It has a lower bound and it has an upper bound. Unbounded if it's not bounded. So that means it could be bounded just above, or it could be bounded just below, or it could be not bounded above, neither below. So if it's not bounded, that means it's unbounded. Then we define the increasing and decreasing sequences. A sequence an when from n equal 1 to infinity is called increasing if for all n greater or equal to n0, an is less than an plus 1. Okay, so what does it mean? This means that you may have, let's say, you know, again, if I want to graph a sequence, it's actually just a list of points. Suppose I start with, this is a1. Okay. You know, we said it's like a sequence, so for 1 I get a1, for 2 I get another number a2, and so on. Okay, so I'm gonna put some numbers here. Let's say that I have this. So these are the terms of the sequence. Now, as you can see here, my sequence goes up, down, up, down. So I cannot say it's increasing, but hold on, this is an infinite series. This is an infinite sequence. I have infinitely many. So maybe now the sequence will keep increasing in this way. Okay, so that's what I mean by n0. If there exists one number, so that after this number, okay, an, if you take any number here, let's say an, okay, so n plus 1 is going to be maybe right next to it. You can see that an is less than an plus 1, and so on. Okay, so when I say the sequence is increasing, similarly as I will define decreasing, it doesn't mean that it's increasing from the beginning. No, it could go up, down at the beginning. Maybe it's not going to have a constant behavior, but after some range, after some number n0, this n0 could be really large. Okay, after that point, it will have one behavior, which is either increasing or decreasing in that case. So this is when I call the function increasing if after n0 it will keep increasing, and I call it decreasing if after some n0 it will be decreasing. Okay. We do have some techniques to tell whether a function is going to increase or decrease. Some techniques they use algebra, easy. Sometimes we might be forced to use calculus, okay? Because you know in calculus you learn like when is the function increasing and when is decreasing. So sometimes we may use this technique. And finally, we said that a sequence is monotonic, okay, if it's either increasing or decreasing. So when you say it's monotonic, then it could be increasing or decreasing after n greater or equal to 0. But maybe they don't specify whether it's increasing or decreasing. Okay. So here's an example on how you can see that a sequence is decreasing using algebra. If I consider the sequence an equal 3 over n plus 5, this is a decreasing sequence for the following reason. If you look at an and if you look at an plus 1, so this is an and this is an plus 1. If you compare them, you have the same numerator, but the denominator of an is smaller, meaning that the fraction is bigger. And actually, this is true for all n greater or equal to 1. So this is like my n0 in my definition. So here we say that the sequence is monotonic, and the sequence is in particular, it's decreasing. Okay, so since an is bigger than an plus 1, then the sequence an is decreasing. So here I am saying also that it's bounded because you can see that it's bounded above and below. It's bounded above by, well, you can have more than one bound above. Okay, you can say any number bigger than, I think, 1, because the biggest value actually is a1. a1 is 3 over 6, which is 1/2. And then we are saying that an is bigger than an plus 1 for all n greater or equal to 1. So certainly a2 will be smaller than this, a3 will be smaller, and so on. Okay. Moreover, you can see that my input is always positive. Okay, and the output will always be positive because it's 3 over n plus 5. So that means I can see that an is bounded between two values actually. It's bounded between 0 and 1/2. This is the lower bound, and this is the upper bound. So it's bounded below and bounded above. So that's why I can say that it's bounded. That means it's bounded below and above. Yes. Now, if the sequence an converges, then it's bounded. Okay. Here I want to show you a very nice, a very important example, and this proves that the converse of this theorem is false. Which means, so here note, and this is very important, caution. The converse. Now the converse means the following: that if an is bounded, then an converges. Okay, the converse is false. Okay, and here's a really nice example that you can see. Consider an, which is minus 1 to the power n. Okay, what's this sequence? Well, this sequence is actually the following: a1 is minus 1, a2 is 1, minus 1, 1, minus 1, 1, and so on. It's gonna keep. I mean, when n is odd, it's gonna be minus 1. When n is even, it's gonna be positive 1. So you can clearly see that this sequence is bounded. Okay, and it's bounded by 1 and minus 1. But is it convergent? No. an equal minus 1 to the power n does not converge. The reason why this does not converge is because the sequence, this is very similar to the idea of cosine and sine. Why the limit does not exist? Because cosine, sine, they keep oscillating. Okay, so they don't approach a single value. The same thing is happening here, because an equal negative 1 to the power n, this is going to keep changing between minus 1 and 1. As much as n is going to be big, that's going to be always the case. It's going to be minus 1, then 1, minus 1, then 1. So it does not approach a single value. So for that reason, an equal negative 1 to the power n does not converge. Okay, this is a very important example. and so you have to be very careful about this. Now we state one of the most famous theorems here. Its proof is really hard. We do not provide it in this course. This says the following, that if, you saw in the previous example that bounded does not mean converge. But if you know that it's bounded and monotonic, then it's convergent. That means if it's bounded and it's increasing, or if it's bounded and decreasing, then I can guarantee that it's gonna converge. Okay. Here you can see that my function was not increasing or decreasing because it increased, decrease, increase, decrease, and so on. So it doesn't have a range where after that range it will be always increasing or always decreasing. So here's a question. Use the monotone convergence theorem to show that the sequence an equal 4 to the power n over n factorial converges. Okay, so I will leave this as an exercise. So try to show that. Okay, I'll give you just some hints here to show that. An is this is actually decreasing. To show that an is decreasing, okay, find this ratio an plus 1 over an and show that this is less than 1, because if this is the case, then this is going to imply that an plus 1 is less than an. Okay, so that means when the numbers are getting big, the terms are getting smaller. This is how you can show that it's decreasing. So just simple algebra here should be enough to give you this result. And then you can clearly see, so this is decreasing, so this is going down, and you can clearly see that this is bounded by 0. Okay, so an is bounded by 0. So I know that there's a limit. They didn't ask you to find the limit here, by the way, but we know the limit is going to be 0 because I gave you that theorem, limit of xn over n factorial is equal to 0, no matter what x is. But here we are doing this using the monotone convergence theorem. Determine if the following sequences are monotonic and or bounded. Okay, so let's take a look at the first one. You can see that an is equal to negative n squared, n is greater or equal to 0. So maybe you would see it, but I would prefer to write some terms here. So for that one, my first term is going to be, actually this is starting at 0, so that would be 0. Then I'm going to have minus 1, then minus, because remember the minus here is outside, then minus 4, then minus 9, then minus 16, and so on. So you can see the pattern here. Is it bounded? No, it's not bounded. Maybe it's bounded above by 0, but it's not bounded below. So I cannot say that it's bounded. Okay, so an is not bounded. Now, is it monotonic? So is it always increasing or is it always decreasing? Well, we can clearly see that this is always decreasing. Okay, so this is always decreasing, so it's monotonic. Another way, this is just extra. How can I show that a sequence is monotonic, increasing or decreasing? For example, if I look at an equal negative n squared, again, you can do it using algebra, like I showed you earlier. Look at this. F of x equal minus x squared. Okay. And I know here that x is greater or equal to 0. Okay, let's find the derivative. What's f prime of x? That's negative 2x. Now, when x is positive, this is negative, always negative actually. in that case, as long as I know that x is greater or equal to 0. So if f prime of x is negative, that means the function f is decreasing. So that's another way to tell whether it's decreasing or not, other than just listing the values. Okay. Now, for that one, I think I mentioned this example, and it's the same as an equal negative 1 to the power n, same idea. For that one right here, I can do this using algebra, and I can also show that it's whether it's increasing or decreasing using calculus. Okay, so using algebra, I'll show you two ways. First of all, this is bounded. Okay, the reason it's bounded is the following. I know that this is always positive. Okay, so I know that it's bounded by 0 below. And I also know another thing. This is n over n plus 1. When you have a fraction, the numerator is positive, the denominator is positive, and you know that the top is smaller than the bottom. The numerator is smaller than the denominator, then the function, the fraction is going to be always less than or equal to 1. So this is bounded. Now I want to see, is this going to increase or is this going to decrease? You can list some values, that's going to give you an idea. But to prove it, you have two ways to do this. Maybe three ways if you want. I can add another one. I can use algebra here. Algebra. I can show that an plus 1 over an is less than 1. So an plus 1 over n plus 1, that's equal to n plus 1 over n plus 2 divided by n over n plus 1, which is n plus 1 over n plus 2 multiplied by n plus 1 okay over, so this is multiplied by n plus 1 over n. So this is equal to n squared plus 2n plus 1 divided by the bottom, which is n squared plus 2n. Oh, well, I can see something here that the top is bigger than the bottom. Okay, so this seems that it's bigger. So this is bigger than 1. So that means an plus 1 is bigger than an. So this means that it's monotonic. It's increasing here, well, actually. So then an is increasing. So then an is monotonic. Or if you want, you can use algebra. You can say, f of x equal x over x plus 1. Then f prime of x, let's see what's f prime of x. Using quotient rule, the derivative of the top is, so here, or you can use this. Derivative, that's 1 multiplied by x plus 1, so x plus 1 minus x. Okay, so the derivative is just x over x plus 1 square. Okay, so if you do the algebra here, this is going to be just 1 over x plus 1 square. That's positive. So then f of x is increasing. If f of x is increasing, that means that the sequence is increasing as well. And then it's monotonic. So I can conclude, and that's easy to see. I don't need to apply the theorem here. But for that one, an equal n over n plus 1, I see that it's bounded. I see that it's monotonic. So I guarantee that it's convergent. Here I know the limit. I can find the limit without using that theorem because the limit is equal to 1. So I know it converges.